one today. So we're continuing on a tricky identities lesson. So what we were doing yesterday was we were looking at the trig identities. I should remind you of them. That's what I should do first. So the trig identities, because it's good to have them in your mind. A very popular one is the trig identity, tan theta equals sine theta over cos theta. We proved that last lesson. The Pythagorean identity, like cos squared theta plus sine squared theta minus 1. You could also use sine squared theta plus cos squared theta minus 1. It's the same thing, but you couldn't reverse these, of course. And then there's all the double angle formulas. The double angle formulas, sine 2 theta equals 2 sine theta cos theta. That's easy enough. What can be a bit tricky is that there's multiple cos double angle formulas. So sometimes if it's a cos double angle, it's like, which one's the best one to use? Can be a bit tricky. But to be honest, in theory, all of them should work. But maybe one of them means less work for you, but we haven't done a problem with that yet. Okay, so cos 2 theta equals cos squared theta minus sine squared theta. Or it also equals 2 cos squared theta minus 1. Or it also equals 1 minus 2 sine squared theta. Sometimes you feel like me, you can by accident miss the squares and stuff, so be really careful when copying down a trig identity. Like you might zone out and forget to put the squares in like I do. Or put a square where there's no squares.
Bathsheba. Thank you. Why can't be 7 for our marks?
Yeah, so then we proved those ones and stuff like that. And then we did these little practice ones. So we were talking about, this one was between 0 and 90. We're still to do the tan one down the bottom. So just reminding you of the question. The question told you that given that cos theta is 4/5, and that theta is between 0 and pi over 2, which is 90 degrees, quadrant 1. So sine and cos are both positive, and so is tan in quadrant 1. Work out these things. So we worked out that sine theta, using this, we plugged it into the Pythagorean identity and rearranged to solve for sine, and we got lovely sine theta equals 3/5. And it makes sense, and we make it positive because sine is positive in quadrant 1. So we found sine of 2 theta. So if theta was doubled, what would be the value of sine? It would be 24 over 25. We plugged it into the, what's it called, the double angle formula, and so on. And because if whatever the angle is in quadrant 1, if you doubled it, it'd still either still be in quadrant 1 or it'd be in quadrant 2. Like if theta was 30 degrees, if you doubled it, it would be 60. It would still be in quadrant 1, so that's why sine's positive. But if it was sine 70 degrees, if you doubled it, it would be 140. It'd be quadrant 2. But sine is also positive in quadrant 2 anyway. So that's why it's definitely a positive answer, because if you doubled the angle. So sometimes people are confused why, oh, when I doubled the angle, I got a negative answer sometimes. So I'm just pointing out that sometimes when you double the angle, it would have ended up in a different quadrant, and that's why it's possible to have gotten a negative when it's a double angle kind of question, because sometimes that comes up, but it didn't in this one, because quadrant 1 and 2, they're both positive anyway. Hang on, I thought we did cos theta already.
No.
Cos 2 theta, okay, I totally dreamt that. So cos 2 theta, double angle formula. You've got to pick, this is the one where it's like, which one? So in theory, all of them should work. Let's just go with the first one, because this one's easy to use because we know cos theta and we know sine theta. But we also know cos theta, so we could have plugged it in here, and we also know sine theta, so we could have plugged it in there. So because we know cos theta and sine theta, we could use any one of these. If we only knew cos theta, which one do you think we would use? The first, the second, or the third?
If you knew what? Second.
Yeah, if we only knew what cos theta was, we'd use the second one, wouldn't we? Because that'd be the easiest. If we only knew what sine theta was, which one would we use to get cos 2 theta?
The bottom one?
Yeah, the bottom one, yeah. So just pointing out that sometimes one of them's faster, so that's why certain ones get picked sometimes. So at this point, we know cos theta and we know sine theta. So to be honest, you could use any of them. I'm just going to use the first one, just because it's the first one. Woohoo! Nice. Feel free, if someone wants to experiment and use one of the other ones, you're welcome to as well, and we'll see that we get the same answer at the end. So that's it. So because it's got the 2 theta in there, you're going to use a double angle formula. So what I'm trying to write here, so you can get started on it, I'm just going to write double angle formula for cos, because of the fact that it's cos 2 theta. Means that, of course, that's the one that we use. Whenever you see these 2 thetas or cos sine 2x's, you tend to, in your mind, start to think double angle formula. It starts to be a thing you start to think about. So double angle formula for cosine. Right. So just pointing out that that's a thing we're going to use. And my reason why I picked the first one is because it's easy enough because we know sine theta and cos theta. So I'm going to write as we know sine theta and cos theta. I'm going to pick this one. What was it again? Cos 2 theta equals, which one's first? Cos squared theta. The order is important because when you subtract, if you reverse the order when subtracting, you get a different answer. So the order is important. So make sure they're all in the formula booklet, so make sure you copy them down super carefully because you could by accident miss the squares or something like that. Sometimes, like I do, I zone out and just don't write it. And this is nice enough. So what is cos 2 theta according to the question? Oh, sorry, what is cos theta according to the question?
4/5.
4/5. So what have I forgotten to do so far?
Square.
Square, yeah. Because it's square. Square. What's sine theta?
3/5.
5, yeah. And if they happen to be negative, just be mindful of that. If they were negative, you'd put them in as negative. But to be honest, when you square a negative, it doesn't come out positive anyway. But for the purpose of the working, just be aware of that. What's 4/5 squared?
60.
That's what. What's the minus? What's 3/5 squared?
9/25.
And what's 16 over 25 minus 9?
7/25.
Cool. So if anyone happens to have the time and energy to want to experiment with the other versions, like one of the cos 2 theta, the double angle formula for cos, if you subbed it into 1 minus 2 sine squared theta, so sine squared theta, you worked out is 9 25ths. What's 2 times that?
18/50.
Close? It's like 2 over 1 times 9 over 25. Yeah, 18 over 25, yeah. So if it was 1 minus 2 sine squared theta, just you don't have to write this, 1 minus 2 sine squared theta, just showing you can use the other versions. You get 1 minus 18 over 25, because sine theta is squared theta is that, double it, it's that. And what's 25 over 25 minus 18 over 25? Yeah, so just doing a quick proof for you. And the other one was, I can't remember, what was it, cos squared theta, 2 cos squared theta minus 1. We do the same answer too. So cos squared theta is that, which becomes 16 over 25. If you doubled cos squared theta, what would you get?
32.
Yeah, 32 over 25 minus 25 over 25. What does that give you? 7 over 25, yeah. So just finding out that they gave you the same answers. The reason why we pick certain ones sometimes is, in this case you could have picked any, so I just personally picked the first one, because it was the first one. But if you only knew cos, you would use the cos version 1. If you only knew sine, you would use the sine version 1, because it's faster. Yay. And then tan theta. In quadrant 1, is tan positive or negative?
Quadrant 1, 10.
Yeah.
Oh, positive.
Positive, yeah, because it's sine over cos, and sine is positive, cos is positive. So which trig identity do you think you'll use for tan? There's only one, really.
Trigonometric.
Yeah, the first one, the trigonometric identity. So just in case I got all of these things, so use the trig identity. What is a trig identity? Tan theta equals?
Trigonometric.
Remember what it is?
Sine squared over cos.
Yes, sine theta over cos theta. Opposite over adjacent. Nice. And we know what sine theta is. What's our sine theta?
3/5.
Nice. And what's our cos theta?
4/5.
Different colours. 4/5. You could start to set it up like that if you want, or you could write. Some people just like to go 3/5. So some people like to go 3/5.
Times 5/4.
Yeah, 3/5 times 5 over 4. Or some people like to write it like that to start with, and then do that step that Sarah said. So if you, it just goes out of whack as you're doing the lesson. It's weird. Yeah. Oh yeah, I need to scroll down, don't I? So some people, instead of the fractiony version, some people like to do this version. Just pointing it out because it makes it easier for them to realise. Keep changing.
It's really good. I used to watch your study.
Yes. Probably got the answer already. So feel free to practice doing your dividing fractions. While we're waiting. You're not ready?
I'm behind on so many shows. Riverdale, White Lighters. I know that. So good. You know it's not again.
Okay, is that our answer?
No, it's not. You can see order. I either 7 or 5.
Real 7, 4. That's good, yeah. And just double check, yes, 10 is positive in quadrant 1. So sometimes I'll just make it up, have a little critical analysis. Makes sense as 10 is positive in quad 1. Sometimes good to critically analyse your answer because sometimes maybe it's not. Maybe we're in quadrant 2 and we should have made 10 negative. I tend to work out the answer and then decide is it positive, negative sometimes, or whatever, for the sign parts anyway. To leave?
That's a mess up with you. I didn't see it. What? Like what?
It's the A1. I yeah.
I stopped Advil when I forgot it.
You're writing it? No, okay, we haven't done it.
Wait, yeah, I forgot it. Oh, I know about it. No, please. If you catch it, then you always
Here we go, another one. This is all non-calc, so you want to be really good at your triangle stuff, which you guys are getting very good at that. So, yeah, you know, the special triangles, the two special ones, the 30, 60, the 45 one. Okay, given that sine theta is negative 3/5, and theta is between pi and 3 pi over 2, find the exact values of, like the non-decimal.
270, is it?
Yeah, good. So that's 270. Yeah. So it can be a good idea to, like, in your mind, just be aware what this means in degrees, if that's easier for you.
So it's between 180 and 270?
Yeah, good. Between 180 degrees and 270 degrees. And then we think, what quadrant is that?
3.
Yeah, good. That's quadrant 3. Sometimes I make a little summary of what's positive then, what's negative then. Or you can do it in the question, that's fine.
It's negative. Wait.
Yeah?
Yes.
Cos is negative and sine is negative and tan is positive, yeah. So for the regular theta ones, that applies. But just be aware, sine 2 theta, if you double something in quadrant 3, the angle could end up in quadrant 1 or 2. So you might get a positive. The sine theta for the 2 theta, that's fine. Anyway, when we do sine 2 theta, I'll explain that one. So given that sine theta is negative 3/5, so that's why sine theta is negative 3/5. When I wrote this question, I by accident made it positive 3/5. Then I was like, no, I have to change that because it's quadrant 3. I had to make it negative. So yeah, so find cos theta. Because you've got sine, and you want to work out cos, I'd suggest you don't know tan. If you knew tan, you could use the trig identity. But because you only know sine, I'd use the Pythag identity.
Okay.
Which is the one that's like, yeah, exactly. It's kind of like a squared plus b squared equals c squared and so on. So use the Pythag identity one and just plug it in. Plug it in. So I'll start to rearrange it, so I can't write very big on this. So cos squared theta equals 1 minus negative 3/5 squared. You can, I would, if I was writing this on paper, I would just plug it into the straight formula first. Yeah. But I have to write big on the board, so I've got limited lines. Being lazy, eh? Yeah, I would have, so if it was me on paper, when I did it on paper, I just plugged it straight into the formula first. Because that makes it really easy for the examiner to give me my method mark, because they don't want to think too much and try to unscramble what I've done. If I just plugged it straight to that, they can easily, bang, go quick. Give me that method mark. Cool, and then we start to work it out. What's negative 3/5 squared? Oh, actually, How close is it? Positive or negative?
It's subtract bracket 9 over 25.
Yeah, exactly. Yeah. Exactly, because that thing becomes a positive, and then it's minus that answer. Minus 9 over 25. So 25 over 25. And I'm doing a bit of space. Cos theta therefore will be the square root of that answer. What is 25 over 25 minus 9 over 25?
16 over 25.
Which is, and then remember you can break up the square root because they're both square numbers. Just be aware they might both be square numbers, and you can break up the square root then. So cos theta. When you take a square root, remember there's a positive and a negative answer.
That's a great point.
4 over 25. So I'll make a point of saying both of them for now. And then you've got to say which one makes sense according to your quadrant.
That.
Yes, thank you. Yeah, so what were you going to say, Krista?
I was going to say, because we're in quadrant 3, cos is negative.
Good, yeah. So which one do you accept as being your answer?
The second one.
Yeah, exactly. So I'll cross out that one and accept this one. So as cos is neg in quad 3. So I just like that, yes, there is a positive and a negative, and you just want to decide which one it is. Brilliant. Cos is neg. I like the double angle formula for sine because there's only one version of it in our course, which is nice. The double angle formula. Let's quickly write it. Double angle formula for sin sine. What is it? Sine 2 theta equals?
2 sine theta times cos theta.
Good. Yeah, 2 sine theta cos theta. I quite like this one. I don't know why. We know sine theta and we know cos theta because of the previous question. So let's plug it in. This is lovely. So you're going to be good with the fractions. What's sine theta? Good, yeah, it's a negative. So the signs are really important because you're not squaring or anything. So the signs are very important. What's our cos theta?
Negative 4 over 5.
Yeah, good. Because in quadrant 3 they're negative. So both are negative. You can work it out whichever way you like. I tend to do equals 2 and I work out what the two fractions are multiplied together first. That's just my way. Good, yeah, because a negative times a negative is a? This is where it can be really fiddly, so like you want to be really careful with stuff like that. Like signs are all very important. And what's 2 times 12 over 25? Is it 24 over 50?
No. He's trying to make fun of me.
No. A lot of people do it, so that's why I'm just trying to generate more memory of it through repetition. But 24 over 25. So sometimes people look at that and go, hang on, we're talking about quadrant 3 for the whole problem.
Double.
Yeah, it's doubled. So say, for example, if the angle in quadrant 3 could have been something like 200 degrees, if you doubled it, what would it get?
I'm sorry, what?
Like say, for example, you know quadrant 3 is down here. So between 180 and 270. So let's pick an angle that's nice and easy, like 200 degrees. So if you doubled 200 degrees,
400?
it's 400, which is like 360 plus
40.
40, yeah, so it could land in quad 1.
What's the point of doubling it? Yeah.
Ah! I don't know. I normally can come up with something for you in terms of a real life application, but this one I'm struggling. I think it's just geometry. I'll see if I can find one for you. You've challenged me, so I'll see if I can find for you. On the top of my head, I don't know. I think it's just geometry for the sake of geometry. But perhaps there is a real world application to a double angle formula. I'll see if I can find one for you. Okay, so yeah, so maybe let's make a point. Okay, to be pos as doubling an angle in quad, doubling an angle from quad 3 be 200 degrees could end up in quad 1. Or another quad. In G quad 1.
But yeah, why does that even matter?
Just because like someone might look at this and go, oh, sine's negative in quadrant 3, and by accident make this a negative. But just trying to justify why don't freak out for the double angles if the sine comes out.
Oh,
what it was in
double.
quadrant. Yeah. So that's really common. Like some people will look and say, oh no, but sine's according to the thing it's in quadrant 3, but when you double it, quite often you'll land in another quad. It's possible to stay in the same quad even, like if it was, as we said, 30 degrees, you double it, at 60 it's still in quad 1. If you had a, let's say a big one, 260 degrees, what's double 260 degrees?
520.
520, which is like 360 plus.
160.
Oh, so would that be in quad 1 or quad 2?
20.
Yeah, quad 2. So just be aware, it could also land in quad 2. But because it's sine, that's why sine is positive. I suppose they could also ask you, like, what quadrant did it land in or something based on something, if it was cos, I don't know. Is anyone writing that green stuff still? And then we have to solve the equation. Oh, I'm giving you a different problem now. Sine 2x equals sine x4. So what quadrants are these?
All of them.
Oh, 4 quads, yeah. So I like to make little notes about it because it makes me think about it more if I write it. And then I'll remember it more. All 4 quads. Yay. The little clue is there's actually going to be 5 answers to this question, but like x equals, x equals, x equals, because of the fact that it's 4 quads. Whenever I see sine 2x, because now you're like, what strategy do I use? Oh my goodness, sine 2x equals sine x. When you see sine 2x, what do you automatically start to think of? Yeah, good, double angle. I tend to think of. Sometimes for this, you're going to have to be sort of experimenting a bit. The double angle formula, by the way, is sine 2x equals 2 sine x cos x, because it's all in terms of x, that's why I'm not using theta. So let's rewrite the equation. Let's put in, so sometimes here you're just experimenting, you do sort of like blind experimenting, but double angles tend to be things that I go straight to kind of subbing in. The great thing is there's only one double angle for sine. So maybe we'll replace this thing with 2 sine x cos x, and then equals sine x. So just pointing out that thing we've subbed in. So this is kind of like a blind little
What
experiment.
have you stopped there, sorry?
So I've replaced sine 2x with what it equals in the trig identity. So the double angle formula is sine 2x equals 2 sine x cos x. So I've replaced the sine 2x here with 2 sine x cos x. And sometimes you're doing it just a bit blindly, like you're doing blind, like experimenting sometimes. And then you see, oh, can something cancel out and then that I can solve?
Mm-hmm.
So this is where it gets kind of creative and interesting. This is where the fun stuff kind of starts to happen. So what could you do? How could you? So sometimes you're thinking, oh, what could I do? Could I divide both sides by sine? What could I possibly do? I just don't know. So I would suggest like maybe, like, subtract sine x from both sides is one thing you could do. So 2 sine x cos x minus sine x equals 0, showing that's something you could do. Overall, we're trying to basically solve for x.
Just divide by sine x originally, and then like you end up with cos x equals half, and that's a lot easier.
Yeah, there's also, unfortunately, another factor though, which is sine x equals 0. So you would get like definitely a few marks for doing that because you'd get all the answers from the cos. But when you factorize this, if you factorize this, you also can take out sine x as a common factor.
Yeah.
So take out sine x as a common factor, you would get 2 cos x minus 1.
So there are multiple ways to solve the problem, but
Yeah.
most of the ways are wrong.
Yeah, like in a way, like you would get part marks because you would get some of the cos answers, but you'll be missing the sine ones because when you factorize like something, this thing equals 0 and that thing equals 0. And therefore, there's going to be answers from the sine version now. That's annoying, isn't it? So you could therefore break it up. Sine x equals 0 and the other thing equals 0. 2 cos x minus 1 equals 0. Of the pain. So you might want to make a point that he's factorizing. Factorize and solve, and then you study to solve. So interestingly enough, sine x is 0 using our little thing, a circle for jiggy. So sine of x is 0 means that it's got no height. So which 2 points, we're doing all 4 quadrants, so it's nice and open. Which 2 points could the point P be to make the height 0?
0 and 180.
Yeah, 0 and 180.
And 360.
And 360, good, yeah. Because it includes 0, obviously includes 180, and it also includes 360. So there's actually 3 answers for that one. So x equals 0 degrees, x equals 180 degrees, x equals 360 degrees. Holy moly. So there are your 3 answers from the sine part. And now we're going to get 2 answers from the cos set as well. So it's getting a bit complicated. So let's start. So this one we might need to rearrange and solve it. 2 cos x equals 1. So what does cos x equal therefore? A half, yep. And what's a special triangle you can use to solve for x?
Always, no, the 30-60.
Yeah, the 30-60 will get you a 1 and a 2. Good that you didn't pick the 45. It's 1 and root 2. So I just draw that thing out really fast. 30 degrees, 60 degrees, 1, 2, root 3. And remember, cos is adjacent over hypotenuse. So cos equals adjacent over hypotenuse. In this case, it's got to be 1 over 2. Or cos theta, sorry. Cos theta, sorry. So the adjacent must be 1 and the hypotenuse must be 2. So is it the 30 degrees or the 60 degrees? Good guess.
60.
Yeah, why is it the 60?
Because it's adjacent is 1 and its hypotenuse is 2.
Yeah. So for either way sine of, like, it would have, the hypotenuse is 2. But for 30 degrees, the adjacent is root 3. And for 60, the adjacent is 1. So for 60 degrees, gives you the 1 over root 2. If it was 30 degrees, it would have been root 3 over 2. Confusing, hey? So quadrant 1's part of the answer, so that's great. So let's say x equals 60 degrees. That's our first one. Notice cos is positive, isn't it? So what's the other quadrant where cos is positive?
4.
4, good, yeah. So what would be the angle in quadrant 4? Yeah, 360 minus 60 if you want to write working out 3 equals 300 degrees. Yeah, good. A lot of thinking in that, isn't it? So let's just also write cos is pos in quad 1 and 4. So that's why there's only 2 answers. Confuzzling, hey? Starting to get a bit more in depth.
So what do you mean there are only 2?
Oh, because notice that the cos, when you solve this, you got positive a half. So it's only 2 quadrants where cos is positive. Because the question was defined as being all 4 quads. But we don't work out any answers for these 2 quads because cos would have been negative a half in those ones. So that's why we had to kind of be critical and only have quad 1 answer and a quad 4 answer. So feel free to write lots of other little questions for that. Brain draining, hey? It's again getting even more wacky and creative. This is where it starts to get nice and algebra-y and frustrating at first and satisfying when you eventually are happy with it all. Okay, good. Yeah, so this one, it turned, did put 2 problems there initially, but then it turned out there's quite a lot of working out for this one, so, and it takes up a wide space on your page. Sign, yep, nice. So see, notice you're asked to, in this case, you're asked to prove. So you're not asked to solve, you're just asked to prove that that side happens to equal that side. So basically when they want you to prove these things, you just need to shove in some trig identities, do some rearranging and solving. But the hard thing is working out what trig identities do I put in. I look for the more obvious ones first. Like, is there any ones that are givens, do you think? We'll clear this here. This one is a nice one. Yeah, that one's a nice one because there's only one version of this one, which is 2 sine x cos x. So that's a nice one that I'd sort of start to work with. The first trig identity I would sub in is this thing. Another thing you can also do is you can FOIL this. So we're going to shove in this trig identity, and we're going to set up the double brackets for this side. Yeah, so it's going to be quite wide on the page, by the way. I've got about 1, 2, 3, 4, 5 lines of working out. So double angle formula. So just trying to sort of point out the thinking that we use. So you look at that and go double formula for sine. I'll just show you sine 2x equals 2 sine x cos x. So we're going to replace sine x with 2 sine x cos x. And this we're going to expand and FOIL. Because when I look at ones like this, you're going to expand and FOIL. And when you sub in things like this, you'll probably find you can kind of rearrange, cancel a whole heap of things out. And it'll get smaller and smaller. Like certain things are going to cancel out when you sub in this thing and you FOIL that thing. So you're going to have so much fun doing this. So we're going to go, I love it, sine x plus cos x, close the bracket. It's meant to be a bracket there. Go in there, bracket, FOILed along with sine x plus cos x. So practice our FOILing. Equals 1 plus, and let's plug in that little angle formula, 2 sine x cos x, where, so just for the sake of your notes, you might want to FOIL things like that. And at the moment you're doing a little bit of blind experimenting, you're just really hoping that it's going to come, when you expand and collect like terms, that you'll be able to cancel some things out and solve, is what you're really hoping for. At this point, if I'm doing this, I wouldn't think, hey, this is definitely getting me the answer. I'd be thinking, hey, I'm just trying something out and seeing where it takes me. So we're going to FOIL, so that's how I show you. I'm FOILing everything. What sine x times sine x become? Yeah, good. So, and how do we write that? Good, yeah. That's right, how the maths gods want us to write it. Sine squared x. What sine x times cos x?
Sine x.
Yeah, exactly, the sine x cos x. And then cos x times sine x. Yeah, cos x sine x. Would you agree that cos x sine x is the same thing as sine x cos x? Yeah, so be aware of those two being the same. And cos x times cos x?
Cos squared x.
Cos squared x. So you're probably guessing that on the next one we're going to collect some like terms. Equals 1 plus 2 sine x cos x. There's nothing much we can do with that side at this point. So our next point is to collect these 2 lovely like terms and see what happens.
My stomach is on.
Oh yeah! Sine squared x plus 2 sine x cos x plus cos squared x equals 1 plus 2 sine x cos x. Exactly, we could subtract, see how we've got plus 2 sine x cos x, plus 2 sine x cos x, we can subtract them from both sides.
And regarding identity.
You do! Which,
Is that a proof?
yeah, exactly. Because it's stated, like, you know, it's assumed that we know it's true. Like you don't then need to prove the Pythagorean identity. Like it's assumed that like, if it's in the formula booklet, we assume it's true. So we can therefore, like Sarah said, because it's adding, we can just subtract them from both sides, which disappears, makes that disappear. And you get this lovely looking formula that looks very familiar to you.
No way.
Yeah. And you're not expected to prove the Pythagorean identity at all. If it's in the formula booklet, we assume it's true. There might be a question that says prove the Pythagorean identity in the exam, but that'd be pretty weird.
Gracias.
So, the Pythagorean identity. Which we know is true. So the fact that it reduces down to the Pythagorean identity is enough proof. If it reduced down to one of the other trig identities that we know, then that's also a proof. So again, like me doing this, when I'm doing this step, I have no idea if it's taking me anywhere. I'm just doing it and hoping for the best. And the thing that made it really obvious was a sine 2x. There's very little you can do with a sine 2x, so I would just think double angle formula. And this thing, I was like, and then I started to think, oh, when you FOIL that, you're going to get that thing. But you might not realise that to start with. And then you just really hope it's all going to condense down to something. So that was proved. We didn't need to solve for anything. We just had to prove that the left-hand side equals the right-hand side. I'm good at writing, so I'll just leave that for a bit. The next one's fun too. I love these things. I love these blind experimenting kind of things. Whenever you see tan in there, what's the only identity that's got tan in that course? Yeah, the trig identity, yeah. There are actually lots of other trig identities. We are only expected to deal with the ones in our course. So the nice thing is there's only one tan trig identity. Knowing less trig identities makes it easier to answer because there's only so many it can be that you're subbing. The more you know, the harder it is then to answer because there's more options to sub in. We're going. Here we go. So tan, that's a good sign. So the little tans makes me think of. Oh yeah, definitely, yeah. There's a lot to write. Yeah, no problem at all.
Okay, thank you.
Sure. So whenever you see tannies, I would think of these things, like, you know, what's that thing? The trig identity. What's another thing in here that maybe is a sign that there's another identity to sub in? That makes you think of something. Can anyone see another thing in here that gives a clue of the other trig identity would be subbing in? Yeah, cos 2x, yep. When I see cos 2x, I think, ugh, because there's, as you know, there's 3 different versions of it. So sine 2x is easy. It's like, oh, I have to sub in 2 sine theta cos theta. But for these ones, you have to think, which one is going to be the easiest? So let's write out the trig identity, because that's one thing you're going to need to be aware of. Trig identity, tan theta equals sine theta over cos theta. And then you think double angle. You might want to write them all out. Cos 2 theta equals, what was it, cos squared theta minus sine squared theta. Well, sometimes write them all out.
What is the word before?
Double angle formula, yeah, I'm just being lazy. What's the other one here?
Cos squared theta subtract 1
Okay.
equals 1
Oh.
subtract
Sorry, just wrote equals 1. Minus 1, so equals, yep, 1, subtract.
2 sine squared theta.
Yeah, so we know for sure that there's only one thing that can be subbed in for the tans, but then there's multiple things you can sub in for the causes. So then sometimes you kind of like have them written out, and when let's fill in some of the tan bits and try to think what one might make sense. So let's start to write out this. Okay. 1 plus, and notice it's sine theta. Sine theta of. Okay. So if you did tan squared theta, I might just want to make a point of this. Tan squared theta would be sine theta over cos theta. Ah, why? Squared. Yeah, squared. So in brackets squared, but what does that, how would we write that in a more mathy way? Squared, which equals, so what could it, how would we write it in a more mathy way than that?
Sine squared theta over cos squared theta.
Yeah, exactly. It's like sine theta squared over cos theta squared, which is sine squared theta over cos squared theta. So that's what we're going to replace tan squared theta with. So 1 plus sine squared theta over cos squared theta. And now I've got to close that bracket, don't I? So just put it inside again.
You just like cut it out. I love it.
There you go. So just be wary, is there a square outside the brackets or anything? No, there's not. It's just 1 plus tan squared theta. Maybe leave a bracket open for your cos 2x, because it's times. So maybe leave a bit of space for your cos 2x bit. And then maybe we'll fill these things in and then try to decide which one of these might go there. See, because remember there's 3 versions of the double angle formula. So maybe write in everything you've got first. I don't know much, I'm doing it kind of like this. And then that might give you a clue what one of these is the best one that will go in. And then 1 minus tan squared theta is still over here. Tan squared theta is that thing. 1 minus.
Wait, sorry.
Yeah, I'm gonna say.
I'll write the whole thing first. So you can, might make sense if you see it all first. See, this is, I've just got that in the way. So, see, I've rewritten the whole thing. Yeah.
In the formulas, shouldn't be using x's.
Oh, yeah. Change. So, yeah, that's a good point. They should be all x's. I'll do that on the next line. I'll do it in yellow over the top.
What should be x's?
Yeah,
Oh,
it's
the
x's,
thetas?
not thetas, yeah. Sorry.
Oh.
Sine squared x cos squared x. Yeah, yeah, that's a good point. I better scroll a bit. What was your question, Lauren and Krista, so far?
Why did you leave that blank?
Because they see there's 3 different versions of the double angle.
So should we just write by cos?
Yeah. In place of it, right now.
No, I'll tell you at this point you probably want to sub in one of those.
So
Because
how
here,
come
there's nothing
you
you can do with these. So you've got to put in something. So notice setting them up makes me kind of, sort of sometimes gives me a bit of inspiration for which version's going to go in there. We want to eventually end up cancelling something out. So we want
the bottom one. I don't know.
first one, yeah, could possibly be. There's one on there that's definitely going to do some cancelling out
I
of some
guess the second
causes.
one.
Yeah, by deductive reasoning, yeah, and elimination. Why do you think the second one's maybe a good one? Why don't I, if I
Because it
sub that
has
in,
two
I've got it.
cos in it. Because the cos is in the bottom of the fraction.
That's
so it's
good.
gonna cancel.
Yeah, good. Because see, there's a cos squared theta in the denominator of this. If we times it by a cos squared theta here, the cos squared thetas are going to cancel out. So we want things to sort of start to cancel down a bit.
So why are you writing that in?
I'm just trying to make people think and ask questions.
Okay.
Like, just move on. Okay, cos squared theta minus 1.
It's an x.
Ah! Cos squared x. A lot of work there now. Now we've got a double bracket with 2 things in it.
Foil!
We have to foil. So this is going to be a nice test of your algebra. But the good thing is things will you can, if you want, automatically cancel out cos squared x. And it's fun, fun, fun. So nice. What's 1 times 2?
2.
It's a good one. What's 1 times negative 1? Oh no, that's
Yeah,
1
you
times
got
2
the-
cos
yeah.
squared. Sorry about that. It's because I wrote them
It'd be
so
2
far apart.
cos squared x.
Yeah, thank you. Good. It would be 1 times 2 cos squared x is 2 cos squared x. 1 times negative 1 is a nice one. Negative 1, good. Now the undercarriages one. What's sine squared x over cos squared x times 2 cos squared x?
Sine squared x times
2 sine squared x. I mean, yeah.
x over cos squared
Yeah.
x.
Yeah, you could do it all as a big chunky thing.
This is 2 sine 2x. 2i squared x.
Yeah, yeah. It's going to cancel down to 2 sine squared x. But you could also write it all out. That's a good idea if you want. If you've got the space, just write it all out. So then it would be 2, if you don't want to, that's okay too. 2 cos squared x sine squared x over cos squared x. If you don't want to write all this out, that's okay. I'll just do it because it's an example. So see, they're gone up. So now it's going to become just 2 sine squared x. And then, what's the last thing? Oh, minus that thing times that thing is like minus. What is it? Sine squared. Don't forget the other side. Equals 1 minus. So if you want to, you can just rewrite the whole thing nicely again. So you can do 2 cos squared x minus 1 plus 2 sine squared x minus sine squared x cos squared x equals 1 minus sine squared x over cos squared x. And something can be kind of crossed out at this point. That's
Cos x greater than cos x.
Yeah, you could
Sine
say,
x greater.
yeah, exactly. See, they're both minus sine squared x over cos squared. So technically, you could add that fraction to both sides. Maybe let's do it one step at a time. Rather, there's another thing that cancels, but let's do this one first. 2 cos squared x minus 1 plus 2 sine squared x equals 1. And then something else is going to cancel out. Yeah, what cancels, Kiega? Oh, sort of. Or what can we do? It doesn't cancel, sorry, but what can I do with that 1?
You can put it on the other side.
Yeah, okay, let's do that. Okay, some of that and stuff. 2 cos squared x plus 2 sine squared x equals 2. What do you think it's starting to head towards now?
The Pythagorean identity.
Yeah, exactly.
Divided over by 2.
Yeah, exactly. Divide everything by 2. You could just divide all 3 things by 2 at once. Some people like to just take out 2 as a common factor first on the left side.
Molly, could you move over a little bit?
No. And then some people, it's fine if you realize divide everything by 2, then that's okay. Just go straight to the answer. And then divide both sides by 2. And then divide by 2. 2 cos squared x plus sine squared x equals 1, which is our Pythagorean identity. So you prove it. It reduces to the Pythagorean identity. So just trying to point out how so this thing, by the way, we added that fraction to both sides if you want to make a note of that. So it really does take a little bit of blind experimenting. Looking for a double angle formula is really handy. And any tan ones are easy because you just sub in sine x over cos x. Like it's quite limited for tan. There's one on the back. You're happy to do that next lesson instead?
Oh, yeah. Let's call it.
Let's call it a day. Bit of a break.
Yeah.
Oh, it's slow, isn't it? Yeah, you're right. It's 9:43. Let's call it a day.